All right, good morning. This is our last section for chapter 4. It is morning here. It's like 5 a.m. when I'm doing this recording. It's the last one that we have. So let's get to it and get it done. Okay, we're looking at binomial and geometric probability distribution. So these are two separate ones, both finding two different things. So first, binomial distribution. Binomial distribution is used in basically responses that are either A or B. So there's two options. Dichotomous is how we would say it. Basically meaning that there's two options. Heads, tails, A, B, yes, no, stuff like that. We have a success side and a failure side. Okay, so the four conditions that are needed to be able to do a binomial experiment, we need to know that each observation must fall into two categories, success and failure. There's a fixed number of observations, so you can't just do this as the observations go off into infinity. You have to say there's this many observations. They must be independent, so they cannot affect each other. Just because you flipped a heads the first time doesn't mean that now it's more likely to be tails the second time. For the probability of success is the same for all observations. Okay, so if the probability of each success is the same, going across every single trial that we do. Okay. Now, with this, what we would be doing is we need to know how many, and we need to know the probability of it. We need the parameters of the situation. Now, the way that it would be written is right there, x, x similar b parenthesis np. N is the number of trials, so the first number with this binomial is the number of trials, and the second one is the probability of success. And this should be in a decimal, so it shouldn't be like 40%, 50%. It should be 0.4 or 0.5. Okay, and x is the possible integer, whatever it is. Okay. So let's look at these two examples and see, are they binomial or not? And if they're not, which of the criteria are wrong? So looking at the first one, tossing 20 coins and counting the number of heads. So if you're flipping a coin, is there two options of success and failure? Yes. Heads would be success, tails would be failure. So number one works. Number two, is there a set number? There is. There's 20. You're only doing it 20 times. So number two works. Number three, are the coins independent of each other? And they are, because every flip has the same probability, and that p-value that goes across the entire thing is 0.5. So the first one would be binomial, and we'd be able to do a binomial experiment on it because it falls under those four criteria. And the second one, 5 cards from a standard deck and counting the number of hearts, but we are not reshuffling it each time. So the not reshuffling is the key in this. So let's start with the first one. Is there a success and failure? Yes, it is picking a heart or not picking a heart. Number two, is there a set number? There is, only 5. 3, are they independent? They are not independent because you are not putting them back. And so the probability, the p-value, is changing every single time. Because once a card is removed or once a heart is removed, the probabilities all change. If a heart is removed, then the probability of pulling the next heart has dropped. If another card has been drawn besides a heart, then the probability of a heart has actually increased on that second pull. So they are not independent, and the p-value is changing. Those numbers 3 and 4 probably will violate each other together. Okay, if they're dependent on each other, the p has to change. All right, so let's talk about calculating these binomial probabilities. So let's say we have a true and false test. There's 5 questions on it. Calvin didn't prepare for it, and he just guessed on all 5 of them. So it's just true, false. So there's A, B. So we want to know the probability of him getting all of them right, the probability of him getting all of them wrong, exactly 3 of them correct, and what's the probability that he will pass the quiz, which would be 3, 4, or 5 correct. Okay, so over 50% correct. So the last one is a range of numbers. So before we have any type of formulas, what we would have is we'd have to write down every single outcome. So if you got none of them right, W's are wrong, C's are correct. These would be the different options we have. So all of them wrong, there's only one outcome. 1 correct, there's 5. 2 correct, there's 10. 3 correct, there's 10. 4 correct, there's 5. And then all correct, there is only 1. And as you see, it makes a nice little curve here. Okay, it gets bigger and then it falls back down, and it gets a nice little distribution. The bottom row is the probabilities of each. So as we go back to the problems, if we want to find the probability of him getting all of them correct, there's only one option out of the 32 possible. So it would be 1 out of 32. If we wanted to find the probability of him getting all of them wrong, again, there's only one option out of 32. So it'd be 1 over 32. What's the probability that he gets exactly 3 correct? So that would be px equals 3. There was 10 out of the 32. And then what's the probability that he will pass the quiz? So that means that x can be greater than or equal to 3. And so with that one, since it's a range of numbers with these binomials, you would add each individual percentage up. So x3, x4, and x5, find the probability of each, and then add them up. 10, 5, 1 is 16. 16 over 32 is a 1/2. Okay, so if you have a range of numbers for your probability, you add them together, okay, each individual. Okay, now there must be a faster way, which there is. Okay, you don't have to worry, there is a faster way to calculate this. Some of you might remember it from previous classes, but it's the binomial formula. So if it is equal to a solid number, what you're going to do is you're going to take a combination, okay, of nk or np, it should be nk, and then you multiply it by the probability of success to the power of k, and then multiply it by the probability of it failure of n minus k. Now with this, the k, the exponents, if added together, should equal the total number of trials. Okay. This combination here, this nk, is npr or ncr. It's the combination, okay, which on your calculator you can do it math, go over to PRB number 3, which is ncr. And that can tell you the number of success, because the order in which you get them do not matter when you're dealing with a binomial. You're just seeing how many possibilities is it. Now, to do a binomial, you need to have bins, B-I-N-S. It needs to be a binary trial, needs to be independent, needs to have the number of trials, and it needs to have the same probability of each, B-I-N-S. It needs to follow those rules, okay, which we talked about earlier. So looking at Calvin's example, if we wanted to do it, we'd go 5c3 of 0.5 to the third times 0.5 to the second. So you see those exponents added up get us 5. And we get 0.3125, which is 10 over the number. Now, if we wanted a range, we would find each individual probability and then add them up just like we did before. So you see here's the probability of 4, NC4, or 5C4, 0.5 to the 4, 0.5 to the 1, and 5C5, 0.5 to the 5th, 0.5 to the 0. And you would add them up and you would get 0.5. All right, now on your calculator, there is another way of doing it. There's a second way. If you go second vars on your calculator, and then there's two options. There's either binomial PDF and binomial CDF. Now, these are different and they are used at different times. So make sure you use the correct one when you are calculating this. Okay. So let's talk about PDF first. So this is the probability of a single number. So if you only want to find the probability of a single outcome, you're going to use PDF. When you type it into your calculator and you type in binomial PDF and it pops up, it's going to give you 3 things that need to be plugged in. The first number, if you do not have a fancy page that asks for each individual and you have to type it in by hand. So if you have like an 83 or an older 84 that's not updated, you're probably going to have to type in these numbers. And it goes the probability or the total number of trials you're doing, comma, the probability of success, comma, what value you're trying to find the probability of. Okay, so Calvin getting exactly 3 right, we would use a binomial PDF, and it would be 5 total number of trials, comma, 0.5, his probability of getting each question right, comma, he wants 3 correct. And we would calculate that out and we get 0.3125. Same as we did before. This is just another way of doing it. Okay, so there's different ways that you could do this. You could do it by hand, writing it all out. You can use the formula, or you can use the binomial PDF to be able to get it a little faster. Okay, now binomial CDF. So now this one is, the C is cumulative, so that means you're looking for a group of numbers. Now your calculator will always do x is less than, x is less than or equal to k. Okay. So it's always going to do x is less than or equal to k when it's doing the computation. It's not going to do greater than, it's always doing less than. Okay, so that's important to remember, it's always less. So if we want to do a range of it, but the NPK are the same, trials, probability, what number you want. Now, if we want to find the probability that Calvin passes, we want it more than 3, more than or equal to 3. So since CDF only does the lower half, we'd have to go 1 minus the probability of him getting 2 or less. Okay, because we can't go greater than 3, so we have to go less than 2 and then subtract 1 from it, because 1 is the entire thing. So if we added up 0, 1, 2, 3, 4, and 5, we should get 1, which we did. So with CDF, it's always less than. So if you want something greater than, it has to be 1 minus. So 1 minus the binomial CDF of 5.5 and 2 is a 1/2, which is what we calculated earlier. Okay. So if we have if we have x is equal to a binomial distribution of 5, 0.4, so that means it's 5 trials with a 0.4 probability. If we want to do this by using the CDF, x is less than or equal to, since it's x is less than, we don't have to do the 1 minus calculation, because the CDF is already calculated in as a minus, or less than. So it's x is less than or equal to 1. We just have to go CDF 5, 0.4, 1, boom, got your answer. Okay. Second one is if it's greater than or equal to 4, and so we would go 1 minus the probability of x is less than or equal to 3, because we just go 1 less. Now, these are usually going to be nice whole numbers because you can't have like a half trial. And so 1 minus the CDF of 5, 0.4, 3 gets us 0.087 as our answer. Okay, finding mean and standard deviation with a binomial variable. So to find the mean is fairly simple. It's n times p. Number of trials times the probability of each one occurring. So since there's a 50% chance of Calvin getting this question right, he had 5 of them, he should get approximately 2.5 correct. And that's why you see the one that's most common from when we wrote out all the possibilities, 2 and 3 were tied for the most common, because it's the average of those two, which would be 2.5. To find the standard deviation, you take the probability that it occurs, the probability that it doesn't occur, and multiply it by the number of trials, take the square root of it. So Calvin had 5 trials. The p-value, the probability of him succeeding, was a half. The probability of his failure was also a half. Take the square root, 1.25, or 1.12. That would be your standard deviation on his quiz. So he could get anywhere from over 3.5 to under 1.5. All right, so now we have geometric distributions. Okay, so we have geometric distributions that we're going to be looking at. So we're moving away from the binomial into geometric. So the comparison between them, a binomial is used when you want to find the probability of something occurring in a set number of trials. So I need this to occur 3 times in 8 trials. Okay, or I flip a coin 10 times, I need 3 heads. What's the chances of that happening? What's the probability of that happening? That's the binomial that we just went over. The geometric probability is used if you want to see how long will it take for this event to occur. So if I'm flipping a coin, what's the chances that I get a one heads in the first 3 flips of the coin? So if I flip a coin, what's the chances of it being heads within the first 3? Okay, and then you find that probability. So binomial uses bins, B-I-N-S. Geometric use bits, B-I-T-S. So again, this is very similar. The only difference is that n. So it needs to be binary. Okay, so it needs to have that yes/no probability. It needs to be independent. Okay, so the trial still needs to be independent, but instead of the n, which is a set number, t is the number of trials until you have a success. Okay, so t is the number of trials until you have a success, and then s is the success probability. So the p-value doesn't change as we go along. The probability doesn't change. So that's the difference. Geometric is looking how long does it take for it to occur the first time. So I have a 6-sided die, and we're going to say y as the number of trials until I roll a 6. So the probability of rolling a 6 on the first trial is 1 in 6. Fairly simple, right? So it's 1 in 6 in the first one. The probability of rolling it on the second trial, so not the first, but just the second, would be the probability of failure the first time and then success the second time, which would be 5/6 times 1/6, which would be 5/36. And then what's the probability of it being on the third roll? It would be 5/6, 5/6, and then 1/6, because I want it on the third row, not the first or the second. Okay, so this is saying this is when we want it to occur. What's the probability that it occurs then? All right, so geometric probability has the probability of success after p trials, and k represents the trials as success, yada, yada, yada. So the formula for it, if you wanted to find the formula without writing out every percentage. So let's say I wanted to say, this occurs after 12 times. Instead of having to do 12 different equations, we can use this formula. So 1 minus p, okay, so the probability that it doesn't occur, the failure, to the power of k minus 1 taken to the power of p. Okay. Because what we want is we want one success and the rest failure after how many trials we want. So that's why that k minus 1, because if we add k minus 1 plus 1, we get back to k. We get back to our number. Okay. And so that's the formula that we would use. So we need the success of failure taken to the power of k minus 1 times the probability of success. Only once. And that probability of success is only once. It's not any more than that. So let's look at a few examples here. So what's the probability that it takes 5 rolls of a dice to get 6? Okay, so it takes 5. That means that since there's 5 total rolls, you would have 5/6 to the power of 4. Failures 4 times, success once. 5/6 to the power of 4, 1/6. Multiplied together gets us about 0.0804. So the probability of getting a 6 on the 5th roll would be about 8%. There's an 8% chance. What's the probability that a 6 happens within the first 3 rows? So within the first 3, we get it. This is one that you'll probably see more often. And so what you would do is you take the probability of each individual one. Probability of it being on the first, second, and the third, add them up and see what you get. And again, adding them up. So 1/6 plus 5/6 times 1/6 plus 5/6 squared times 1/6 gets us about a 42%. So it's almost a 50% chance that within the first 3 rolls, you would get a 6. Okay. All right, geometric probability on your calculator, second vars, and you'll see you had that binomial, CDF, PDF, and now there's Geo, Geomet, PDF, and CDF. The PDF, CDF is again the same. It's the cumulative and the actual number. So the P is you can think of it a point. That finds it being exact, and CDF finds it being less than a number. Okay, so X is less than whatever the K value is. Okay, so make sure you guys remember to do the correct one. Okay. Okay. So, one of the last things we have here is the mean and the standard deviation using the geometric random variables. To do the mean, it is 1/p, so 1 over the probability of it occurring. And this tells you how many trials it should take for it to occur. Okay. So if something was, let's say, a 0.5, like flipping a coin, there's a 0.5 chance that it would be heads. That means that probably within the first 2, you'll have 1 heads. Okay. On average, the first 2. To do the deviation, it is the square root of 1 minus the probability of success all over the probability of success. Okay, and that's how we would calculate those. Again, it's just a quick formula, just and then you got it. All right. Okay, so you start her old lawnmower. Okay, so to start an old lawnmower, Iris has to pull a cord and basically get lucky. Anybody that's ever dealt with an old lawnmower probably remembers or probably knows that, you know, sometimes it works, sometimes it doesn't, and that's just how it goes. Maybe you have to use a choke, etc. There's a 20% chance that it will work. What's the probability that it will take 3 pulls exactly for it to work? So the probability of failure was 0.8 taken to the second power multiplied by 0.2. Gets us 0.128. What's the probability of it taking more than 10 pulls? Okay, so it takes more than 10 pulls for it to get started. Since it's more than 10, we can use our CDF, our geometric CDF, but we have to go 1 minus, because remember the CDF is less than. Okay, so the CDF is less than a number. So we would go 1 minus the probability of it being less than or equal to 9. 1 minus the geometric CDF of 0.2 comma 9, okay, is equal to about 13%, or 0.134. And then how many pulls would you expect it to be, which would be the expected average, which would be 1 over 0.2, which is 5. Okay, so it should take her about 5 pulls on average to get it started, because it's about a 20% success and failure rate. Okay. All right, that's it. We are done. Congratulations on making it to the end. I hope you didn't do this the night before, because that would just be terrible that you'd had to listen to my voice for so long. All right, so thank you and have a great day.